The world of patch management has many moving parts: systems, vulnerabilities, updates, and processes that all need to work together. To navigate this landscape, it's important to establish a shared vocabulary. Common terminology helps teams communicate clearly, avoid misunderstandings, and align with industry best practices. Alongside terminology are the tools that make patch management possible. From vulnerability scanners that detect flaws to automated deployment platforms that apply updates at scale, these tools provide the foundation for effective programs. In this section, we'll cover the key terms and tools every associate-level practitioner should know. A zero-day vulnerability is a flaw that is unknown to the vendor or defenders, but may already be known to attackers. It's called zero-day because once the vulnerability is discovered, the vendor has had 0 days to create and release a patch. 0 days are dangerous because attackers can exploit them before defenses exist. Once disclosed, vendors race to develop a patch, while organizations scramble to apply workarounds or mitigations. While patch management can't prevent 0 days directly, it ensures that when a patch is released, it can be applied quickly to limit risk. CVE stands for Common Vulnerabilities and Exposures. It's a standardized system for cataloging and naming publicly known security flaws. Each CVE entry has a unique identifier. For example, CVE 2021-34527, which was the Print Nightmare vulnerability. The purpose of CVEs is consistency. Instead of different vendors or researchers describing the same flaw in different ways, the CVE system gives everyone a common reference point. Security tools, vulnerability scanners, and patch management platforms all rely on CVEs to track and discuss issues clearly. In short, CVEs provide a universal language for identifying and sharing information about vulnerabilities. CVSS stands for Common Vulnerability Scoring System. It's an open standard used to measure the severity of security vulnerabilities. CVSS assigns a numerical score from 0.0 to 10.0, with higher scores representing more severe risks. These scores are often grouped into categories: low, medium, high, and critical. The score is based on several factors, such as how easily the vulnerability can be exploited, whether it requires user interaction, and the potential impact on confidentiality, integrity, and availability. CVSS provides a consistent way for organizations, vendors, and researchers to prioritize vulnerabilities. While it doesn't measure how likely a flaw is to be exploited, it helps teams understand the potential impact and urgency of patching. VPR stands for Vulnerability Priority Rating. Unlike CVSS, which measures the theoretical severity of a flaw, VPR focuses on real-world risk. It combines factors like CVSS scores, threat intelligence, exploit availability, and malware activity to produce a dynamic score between 0 and 10. The key difference is that VPR is time-sensitive. A vulnerability with a high CVSS score may not be exploited in practice, while a medium CVSS vulnerability with active exploits may have a high VPR. This helps organizations prioritize what to patch first, focusing on vulnerabilities that attackers are most likely to use right now. EPSS stands for Exploit Prediction Scoring System. It estimates the likelihood that a vulnerability will be exploited in the next 30 days. Unlike CVSS, which measures potential severity, or VPR, which blends severity with threat intel, EPSS focuses purely on probability. EPSS uses machine learning models trained on vulnerability data, exploit databases, and real-world attack trends. The result is a percentage score. For example, an EPSS of 5% means there is a 1 in 20 chance the vulnerability will be exploited in the near term. This makes EPSS especially valuable for prioritization. Security teams can use it alongside CVSS and VPR to decide not just how bad a vulnerability is, but how likely it is to become an active threat. An SLA, or Service Level Agreement, is a formal commitment between a service provider and a customer that defines performance expectations. In patch management, SLAs often specify how quickly different types of vulnerabilities must be remediated. For example, an SLA might require critical security patches to be applied within 7 days, high-severity patches within 30 days, and medium or low-severity patches within longer timeframes. These agreements set clear expectations, provide accountability, and are often reviewed by auditors, regulators, or customers. SLAs ensure that patching isn't just best effort, but a measurable obligation that supports security, compliance, and trust. MTTP, or mean time to patch, is a key metric in vulnerability and patch management. It measures the average amount of time it takes an organization to apply a patch after a vulnerability has been disclosed. A low MTTP indicates that an organization is responding quickly, reducing the window of exposure to attackers. A high MTTP suggests delays, which increase the chance that a vulnerability will be exploited. MTTP is often tracked alongside SLAs and compliance goals. It gives executives, auditors, and insurers a measurable way to assess how disciplined an organization is at closing known risks. Compensating controls are alternative security measures put in place when a vulnerability cannot be patched immediately. Instead of eliminating the flaw, these controls reduce the risk until a patch can be applied. Examples include blocking vulnerable traffic at a firewall, disabling an affected service, increasing monitoring, or restricting access to the vulnerable system. While compensating controls can buy time, they are not substitutes for patching. They are temporary measures that help organizations manage exposure when business, technical, or operational constraints prevent immediate remediation. Patch management relies on a range of tools that help organizations find vulnerabilities, assess risk, and deploy updates consistently. These tools reduce manual effort, provide visibility across large environments, and enforce repeatable processes. At the associate level, it's important to know the main categories: vulnerability scanners that identify flaws, patch management platforms that deploy updates, vulnerability databases that keep track, reporting tools that track compliance, and vulnerability scan analysis tools that tailor data to your particular network. Familiarity with these categories, and with common products used in the field, helps practitioners understand how patch management is put into practice. Vulnerability scanners are tools that identify weaknesses across systems and applications by comparing software versions and configurations against known vulnerabilities. Nessus, from Tenable, is one of the most widely used scanners, capable of detecting flaws across networks and endpoints. Qualys provides a cloud-based platform for vulnerability management and compliance scanning, making it easy to scale across large environments. OpenVAS is a popular open-source option, offering scanning capabilities without licensing costs. These scanners form the foundation of vulnerability management by giving organizations visibility into what weaknesses exist so they can be prioritized and patched. Patch deployment tools automate the distribution and installation of updates across enterprise environments, reducing the need for manual effort. For Windows environments, Windows Server Update Services, or WSUS, is a free option that lets administrators approve and manage updates centrally. System Center Configuration Manager, often called SCCM or Config MGR, provides more advanced patch deployment capabilities at the enterprise scale. For cloud and mobile-first organizations, Microsoft Intune delivers patch management across Windows, macOS, iOS, and Android devices. These platforms ensure patches are deployed consistently, on schedule, and with minimal disruption to end users. Vulnerability databases and feeds provide the authoritative data that both tools and practitioners rely on. The most widely used is the National Vulnerability Database, or NVD, maintained by the U.S. government. It catalogs CVE entries and assigns CVSS scores to measure severity. Another critical resource is the CISA Known Exploited Vulnerabilities Catalog, or KEV list, which highlights flaws already being actively targeted in the wild. These represent top patching priorities. Finally, vendor security bulletins, such as the Microsoft Security Response Center or Adobe Bulletins, provide updates directly from the companies that build the software, often with detailed remediation steps. Together, these sources guide patch management priorities and ensure organizations focus on the most pressing risks. Monitoring and reporting are critical parts of patch management because they provide visibility into compliance, progress, and accountability. Most patch and vulnerability management platforms include built-in dashboards, but many organizations extend this with specialized tools. For example, Splunk is widely used for CM and can correlate patching data with security events. The ELK stack, Elasticsearch, Logstash, and Kibana, allows highly customizable dashboards and reporting. ServiceNow is often integrated with vulnerability workflows, enabling teams to track remediation tasks and provide executives with clear updates. These tools ensure patching isn't just happening. It's measured, tracked, and visible across the organization. Identifying vulnerabilities is only the first step. Interpreting and prioritizing them is just as important. Vulnerability scan analysis involves reviewing scanner outputs, consolidating duplicates, adding business context, and assigning priorities. Without this step, teams can be overwhelmed with thousands of low-risk issues. With proper analysis, focus shifts to the vulnerabilities that matter most. This is where tools like PatchPlan come in. PatchPlan ingests scanner outputs and applies prioritization logic based on exploitability, severity, resources, and business impact. By automating much of the analysis, it reduces noise, highlights high-value remediation opportunities, and generates clear reports for both technical staff and executives. Tools like this bridge the gap between raw vulnerability data and actionable patching strategies. Patch management relies on both clear language and effective tools. Key terms like vulnerability, exploit, CVE, and patch compliance create a common vocabulary that ensures teams communicate without confusion. Tools such as scanners, deployment platforms, and reporting systems provide the structure needed to apply patches consistently and at scale. For associate-level practitioners, the goal isn't to memorize every acronym or master every tool, but to understand the basics, what they mean, why they matter, and how they fit into the patch management lifecycle. With this foundation, teams can align with best practices, work more effectively, and reduce risk in measurable ways. Patch management may sound simple, just keeping systems updated, but it's one of the most critical disciplines in cybersecurity. Section 1 introduced the foundations by explaining what patch management is, why it matters, and the terms and tools that support it. At its core, patch management is the structured process of acquiring, testing, and applying updates that fix vulnerabilities, bugs, and performance issues. Every patch applied closes a door to attackers and improves stability. The urgency is clear. Once flaws are disclosed, exploits often appear within days. History shows most breaches exploit known vulnerabilities that already had available patches. To understand this, we covered the basics. Vulnerabilities are weaknesses. Exploits are the methods to abuse them, and patches are the fixes. We also introduced key terms like CVE, CVSS, VPR, and EPSS, along with metrics like mean time to patch and compliance rates. Tools such as scanners, deployment platforms, and reporting systems make patching scalable and measurable. The main lesson is that patch management is not routine IT work. It's a strategic function that protects security, ensures compliance, and strengthens business resilience. Section 1 built the vocabulary and context that set the stage for deeper exploration of how patching is practiced effectively.